Okay, we're now going to add small animals to our Malthusian model. So we showed that when humans were totally dependent on the megafauna, the big animals, then if humans drove the population of the big animals down, well then the human population fell. As a consequence of that, allowing the big animal population to recover, and you got these cycles. But what if the humans have alternatives to the big animals? That's what we're going to look at here, and the alternative we've chosen, following a paper in the literature, I can't remember the citation, it's Bull, isn't it? I'm not even sure how to pronounce it. Is that we add small animals. So now, Y, which is food production, instead of just being theta n times L, it's now phi n. It's now phi n plus phi s. Remember, n is the population of the big animals, and here s is the population of the small animals. L is how many people there are, and they're assumed to spend their whole time hunting, and these are kind of productivity factors. And we model the stock of the small animals more simply than the big animals. They're assumed to adapt instantly to hunting pressure. So S is S star, which is the carrying capacity, minus hunting, which is phi S times L. Okay. And if we bring this over and divide through, we get that S is actually S star over 1 plus phi S L. Okay, so if there's no humans, S is S star. The more humans there are, the lower that'll be. As the human numbers go to infinity, that'll drive the small animals to extinction. Okay. So, what then do we have for the human population growth? We have that LT plus 1 minus LT is theta L LT. So, again, we could think of dividing by LT, and then this is a sort of percentage growth, isn't it? A fractional growth is theta L times this term. And if this term is 0, then the population is stable. If it's negative, the population is going down. If it's positive, the population is going up. And then we have this 1 minus something. And what is something? Something is y bar over little y. Y bar is what humans need to just keep reproducing, but not to increase their numbers, but enough to keep going. So if little y, big Y over L is equal to y bar, the population is stable. 1 minus 1 is 0, stable population. And we have, if we divide through by L, we have phi n plus phi s. S, but we can replace S by S star over 1 plus phi S L. So actually, let's stick that up there too. phi s s star over 1 plus phi s L. But we can't replace n by a nice simple expression because n evolves dynamically in the way that we already worked out. Okay. So, again, I think we've more or less nailed it here. Let's just take the next slide. Seems like I'm doing some more work here. I'll have to have a look at that. But what's this saying? On the right-hand side here, we've got terms in T and parameters. On the left-hand side, we've got these terms in T plus 1. So these two equations are telling us how these two state variables, n and L, are evolving over time from a given starting point. Okay. So it's pretty straightforward. So how are they going to evolve? That's the next question, which we'll have a look at in just a second. Okay, so how are they going to evolve? What we're doing on this page of the notes is to say, well, how would they evolve in the really simple case when there are no megafauna? N is 0. Okay. So let's have a quick look at that. So we're parking those equations and working up here. And n is 0. So this whole equation just disappears. It's just like 0 equals 0, isn't it? But this one, we can put n equal to 0 in here, and then basically that's it. We've got a new equation, haven't we? Which is then LT plus 1 minus LT equals theta L LT 1 minus y bar over phi s s star divided by 1 plus phi s LT. And then, so this will give us, again here we've got terms in T, so from a given position we'll know what's going to happen, and we can see pretty straightforwardly that when LT is big, this is small, so this is big, so 1 minus this is negative, L is going to fall, you know, it has the expected properties. But we're interested in what's going to happen in the long run. In particular, let's assume that there's some long run state when the population is stable. What is that state like? Well, let's just assume that we're in that state. So this is 0, which means that y bar over this equals 1, which means y bar equals this, right? So y bar equals phi s s star over 1 plus phi s LT. So if we multiply both sides by 1 plus phi s LT and divide both sides by y bar, we get 1 plus phi s LT equals phi s s star over y bar. If we take that 1 over, we get that, and if we divide by phi s, we get that. So there's long run stability L when L is equal to S star y bar minus 1 over 5. So, and obviously this should be positive. So if it's the case that S star y bar is actually less than 1 over 5, then that means there is no stable long-run level of population, which basically means that the small animals are so few or so tricky to catch or whatever it is that humans are going to die out. If that's all they've got to live on, they're going to die out because they just can't catch them quick enough to get enough food to eat. So we've got this condition for a sustainable population that phi s star must be greater than y bar. Sorry, I'm misreading. Look like a G. My terrible eyesight. Okay, let's pause there for a second. Right, and so then the next step is just to run the numerical model, and we can stick in parameters such that this holds or such that it doesn't hold. And basically, if the small animals are enough to keep the humans going, what's going to happen? So here we've got the starting position, lots of big animals, hardly any humans. The humans start feasting on the big animals, their population goes up, the big animal population collapses. What's going to happen now? The humans start trying to live off the small animals. And let me just think about this a minute. Okay, so the dynamics here are kind of interesting. Because in this upper case, the small animals are not enough for the humans to survive on. Okay. So the humans have more or less wiped out the megafauna. And then they're pretty much totally dependent on the small animals. But unfortunately, they can't quite harvest enough of the small animals to survive. So over time, the human population goes down. Meanwhile, the megafauna population is very, very low. But if sufficient time passes, at some point, the human population will be so low and the megafauna population will have had enough time to actually start recovering, at which time we can have a recovery in the human population. Sorry, that's the wrong way around. That's the megafauna and that's the human. So then you're going to get cycles again, and the megafaunal population will be able to survive, although it's extremely close to the edge. But if the humans can actually survive in the long run on the small animals at a significant population, then the megafaunal population will be driven to zero. Notice the way we've actually modeled this, no population will ever go strictly to zero. Okay, because as the population gets very, very small, they get harder and harder and harder to find. Somewhere there's always going to be like one hiding away somewhere and not being found. In practice, of course, once you get below a certain population, they will become extinct because they're kind of lumpy. You can't have a population like approaching zero. At some point, if there's only one individual left, extinction is inevitable. So in both of these models, you could actually have extinction you added the fact that below some population level it's just not viable. Okay, so that's that model. I'm going to stop there because the purpose of this is basically to go through the map.